So, in the name of Allah, the most merciful and most beneficent, today in lecture 8, we are going to discuss some foundations of complex analysis. We are going to consider this into applied mathematics, but we can do it a bit rigor, and we can consider this subject to be in part of pure as well. So, we will not be going in detail so far, but we will be doing the most important results, formulas and theorems in this one. Okay, so the first thing in complex analysis is what we call the complex number or complex variable. So for example, complex number is simply a number z which can be written in this form a plus bi, where I is the square root of minus 1, or in other words I square equals minus 1, and where these a and b are from the set of real numbers. This is what we call a complex number, and if a and b are fixed, we call it a number, and if a and b are itself variables, we call this a complex variable. So there is no any difference basically, but if it is fixed, that is going to be a number. If we are going to variate the quantities a and b, then we call it a complex variable. So the question is why there is a dire need to introduce a new set of numbers, what we call complex numbers. We have so many sets of numbers in the beginning. For example, we started with the set of natural numbers. We know very well these are simply the counting numbers 1, 2, 3 and so on. Then we thought that okay, there are some negative numbers required. Then we introduce a new set, what we call the set of integers. So integers, yes. And these type of numbers help us to solve the equations like this. Like give me a number x, I am going to add 1 to it, the answer is 0, so the number should be minus 1, because minus 1 plus 1 is going to be 0. So there are some equations which are not solvable by natural numbers. Then we introduce a new set, what we call the set of integers. Then we needed another set, what we call the set of rational numbers, all the numbers of the form a by b, and this type of set helped us to solve the equations of this form 2x is equal to 3, because there is no any number x in the set of natural numbers or integers which solve this equation. That number is 3 by 2, and when we plug it in here, it satisfies this equation. Now we saw that this set is very good. It solves lots of problems, but this set is not complete. We have done this in real analysis that a Cauchy sequence in the set of rational numbers does not converge in Q. But you take any Cauchy sequence, it converges in the set of real numbers. So we call the set of real numbers to be complete. So this is not complete. This set is not complete. So basically the property of completeness is not satisfied in the set of rational numbers. Then we introduce a new set, what we call the set of real numbers. And the good thing about this one, it's a field, and field means it's an abelian group with respect to addition, and there are some additional properties as well. And the good thing about this one is it is a complete set. And what do you mean by complete? You take any Cauchy sequence, if it converges in that set, we call it the set is to be complete. Then what is the problem with the set of rational numbers, set of real numbers? Why there is need to introduce a new set, what we call the set of complex numbers? Any idea? The first problem is we can't solve equations of this form. When you solve this equation, it means give me a number, I square it. For example, I can rewrite this into this way. Give me a number, I square it, the answer is going to be minus 1. So there is no such a number in the set of real numbers. It means real numbers are basically not helping us to solve these type of equations. Then we introduce a new set, what we call the set of complex numbers. So set of complex numbers is just an extension of R. By taking R into R means the cross product between R and R, we can call it R2, and RC is simply what we call isomorphic to R2. Because we have a complex number A plus BI, we can write it in the form of ordered pair, and this ordered pair belongs to R2. So we can say that the set of complex numbers is isomorphic to R2. And what is a good thing, we can solve these type of equation in this one. And what we call this basically, we say that the set of real numbers is complete, but the set of real numbers is not algebraically complete. And what is algebraic completeness? Yes. What else? So you have this equation, a polynomial equation, a1x plus a0 equals 0. Let's say this is a polynomial equation, and these AIs means these all are rationals. This is a polynomial equation with rational coefficients. Okay, it is not possible to get the solution of this equation in the set of real numbers. So we say that the set of real numbers is not algebraically complete. It means I give you any equation, I give you quadratic equation, I give you cubic equation, and so on. It is not possible that you can solve each and every quadratic and cubic equation in R. Is it possible? No. You teach first year mathematics, you have seen so many times that we have a quadratic equation. Its roots can be imaginary. We call it the complex conjugate roots. But you take any equation with these rational, the coefficients are rational. You can claim the coefficients to be real, but let us assume the coefficients are rational. Then you can solve each and every equation of this type into the set of complex numbers. So we say that the set of complex numbers is algebraically complete, but set of real numbers is not algebraically complete. Okay, so this was a bit discussion about why we needed the set, what we call the set of complex numbers.
So sir, one question about personal मुख्य पाठ के काम कर रहा है. Field and ring में करो पापा.
There's a difference. I don't know exactly about abstract algebra, but there's a difference. I will tell you. I think in field we have some multiplicative inverses. In ring we don't have. We have both operations in ring as well as field, but in I think field we have multiplicative inverses. It means a field is a group with respect to addition, a Boolean group. It's a group with respect to multiplication as well, but ring is not. Ring satisfies some properties of multiplication, like there is some distributive property, left distributor, right distributor, and so on, but it is not completely a group with respect to multiplication.
We apply both on algebraic equations. How we can differentiate? Have any idea about that?
It means you say that if we take particular example, how can we differentiate that whether this is a ring or a field? In the set of like these infinite sets, it's going to be obvious that whether these are fields or not. But it basically differs when you take a finite set, like in the case of modulos. But we'll be discussing this in abstract algebra if we got time for that. Otherwise, the things in complex analysis are very much, so we need so much time for that. So let us see how much we can do in, let's say, 1 or 2 weeks. But I'll be doing the things from very basic point of view so that you can understand the things clearly. So I have a complex number a plus bi. I define its conjugate in this way, and you know very well it is written like z bar, but sometimes I will write z star. So don't confuse yourself with that one. So it is simply change the sign of imaginary part. Here the real part of z is a and imaginary part of z is b. And what is this z bar? It is just a reflection. But this time reflection in x-axis. So for example, I have a complex number a plus bi. I can say that it's nothing but an ordered pair AB. So this is, let's say, value A and this is value B. So I have this point AB. So this is what we call the organ diagram. So what is Z star? It's nothing but the reflection of this complex number in. So this is Z star and this is Z. This is reflection in x-axis. Then I define the norm or the length of this complex number, or what we call the modulus. That is simply square root of a square plus b square. That is nothing but the length of this. And length of z star in this is this. And you can clearly see that the length of z is same as the length of z star, because it is nothing but the reflection of that. And we can write a complex number in polar form. You know very well, if you have any point in Cartesian plane, you can rewrite this into polar form. Then you say, okay, there are two things. One is the angle theta with the positive x-axis, and another is the length of this particular vector. And the polar form for the complex number is going to be r cos theta plus iota sin theta. And what is r? R is simply the mod of z, and we can say that, okay, this is, we can rewrite this into some short form as well. Cis. Okay, that is c for cos, I for iota, and s and theta. And so this is the short form, but by using Euler's theorem we can write it e raised to iota theta. So this is Euler's theorem. So these are the bit of the things that we should keep in our mind. Okay, what is Euler's theorem? E raised to iota theta is cos theta plus iota sin theta. Sin theta. And what is theta? Theta is any real number. I think it will work for complex as well. So let us keep it same for now. Okay, so here we say that r is simply the mod of z, and what is theta? Theta is tan inverse y upon x, or I think here it would be b by a. Tan inverse b by a, and we call this thing to be argument of our complex number z. What is this? This is modulus, and this is argument of a complex number z. Now there is a problem with the argument. It is not uniquely defined, because when you find tan inverse of something, there are basically infinite values depending upon the period of tan. And you know very well the period of sine and cos is 2n pi, or 2 pi simply, and the period of tan is pi. So when you find this quantity, you exactly add some n pi here. So this theta is not uniquely defined. So that's the problem. That's the basic problem with the theory of complex numbers. And there are lots of things introduced to deal with this particular concept. We have some sort of branch cuts, and we have some sort of principal argument and principal value of logarithm to deal with this kind of idea that we will be discussing in detail. So what is the principal argument?
You can say that the argument of z is not defined, so like the principal argument. You can say that it is a multivariate function.
Yes, that's the problem. That's the problem. So when you find tan inverse, when you find basically theta, it is tan inverse of this quantity, but tan inverse is going to be a number plus n pi. and n is any integer, so theta is not going to be a unique value. There are basically multiple values for theta assigned to it. So that's the problem basically. So how can you find out the principal argument? And principal argument is denoted by this. It is denoted with capital A, and you have the small a here. So this principal argument of a complex number lies always between minus pi and pi. It means minus 180 and plus 180, and you have to include one thing. Either you have to include this one or you have to include this one. But sometimes there are some authors which do not include both of these. But we are going to include pi in this one. And some say that okay, argument lies between, let's say, 0 and 2 pi. Sometimes it is said like that. We are not concerned about this one because mostly it is used like this. So we are going to use this. The argument of a complex number always lies between minus pi and pi. And how can we find this particular quantity exactly? So let us see this thing. So you have to check that where does your complex number lie, and you can see that particular thing easily, because you know very well in first quadrant both quantities are positive, in second quadrant one is positive, other is negative, and so on. So let us make this diagram, and in the first quadrant the argument of your complex number is simply tan inverse b by a. So if the quantity lies in the first quadrant, there is no issue. Just tan inverse b by a, whatever answer you get, that's the principal argument. And if the complex number lies in the second quadrant, then the argument would be tan inverse. Now one thing I am going to take the like absolute value of the both of the numbers, because if I go to second quadrant, one number will be negative. I think it will be real part that would be negative. So I am going to take both positive, and I am going to subtract this quantity from pi. This is my argument. This is my argument. Okay, and in the third quadrant, I am again doing the same thing, tan inverse b by a, and I am adding this quantity to minus pi. This is going to be the argument, and in this one it is tan inverse b by a, but the negative of this one. This is the argument of my complex number if it lies in a fourth quadrant. And one thing can be seen easily, this general argument is same as principal argument plus 2n pi. Principal argument plus you apply rotation to it of 2n pi. Here n is 0 and plus minus 1 plus minus 2 and so on. Then you exactly get the generalized argument for a complex number. Okay, so these are the bit of the things that we should keep in our mind, and we are going to do the things in detail, but stating each and every theorem. Next is very important theorem, what we call De Moivre's theorem. So De Moivre's theorem, what does it say? So one statement is, if you take any n from the set of let's say integers, then what happens that cos theta plus iota sin theta raised power n is same as, just you multiply this n with the angle, so cos n theta plus I sin n theta. So these are always same when n is an integer. Okay, what if n is a rational number? Then what happens? Any idea? Okay, then any one value of cos theta plus I sin theta whole power n is going to be cos n theta plus I sin n theta. Are you getting this? When n is any rational number, let's say it's 1 upon 2. Is 1 upon 2 rational?
Yes, sir.
Of course. Okay. So it means I have this complex number. I am finding its square root. 1 upon 2 means
Yes, sir. Square root.
square root. And how many square roots do you get exactly? 2. Means you have 2 values.
Yes, sir.
Out of those 2 values, one value is going to be not both, but one value is going to be. Because when you have some rational number, you are going to find square root, there will be 2 square roots.
Yes, sir.
Cube root, there will be 3 cube roots.
Yes.
So this is the idea behind that. Okay. Next one is, let us write some properties.
What about others?
What about?
Other root?
We can find other roots by using standard formula, like we'll write here n theta plus 2n pi, and we'll be solving this with the help of that. But this is the statement of De Moivre's theorem. We are coming to that. Okay, how can we find out the n roots,
Yes, sir.
cube roots, fourth roots, and so on.
So sir, you get the argument of the negative करेगा तो due to complex so conjugate.
No, it is because I want this quantity between minus pi and plus pi.
Fourth quadrant, sir.
Yes, that's right. Among these two quantities, let's say one is positive, another is negative, but I am making both of these positive. If I am going to get tan inverse, then if I am going to ignore minus, that would be an angle like 30 degrees or 40 degrees.
Yes, sir.
If you say 30 degrees, it lies in first quadrant. But since the number lies in second quadrant, so I am going to give it minus, so that I am going to come down
Okay, due to direction.
due to direction, the orientation of that particular number. That's why. Okay, so some of the properties are, if you take z conjugate, whole conjugate, that's always z, and z plus conjugate of z is always equal to 2 times real part of z, and you can check these things easily. And number 3, z minus z conjugate is going to be 2 times imaginary part of z times I will be there, and z is real if and only if z is equal to z conjugate. So z is 0 or purely imaginary if and only if z is equal to minus z conjugate. Are you okay with this? Z is going to be 0
Yes.
or it's purely imaginary when this thing happens. You know very well this thing. What about this thing? You know very well that this thing is equal to square root of. So what is this?
Yes, sir.
Is it okay? Square on both sides.
Yes, sir.
What about this? Same thing, we know very well when we multiply these two things, we get this.
Yes, sir.
It means the modulus of z squared is same as z times z conjugate, and we can say that the modulus of z is the square root of z times z conjugate. So when you multiply z with its conjugate, take its square root, you will get exactly the modulus. Okay. Number 7. And there are some similar things. I am going to write only one of these. Like when you Just add or subtract two complex number, take their conjugate. It is same as one complex number conjugated plus minus another complex number conjugated. And same thing applies with multiplication, division, and so on. So I'm not going to discuss these things in detail. Okay, one thing is that triangle inequality. So we know very well that if we are dealing with complex numbers, simply we are dealing with R2. R2 means what we call the Euclidean plane. So we can define triangle inequality in that one. So it is simply, if you take two complex numbers, add them, take their absolute value or take their modulus, it is less than or equal to modulus of Z1 plus modulus of Z2, and is greater than or equal to modulus of Z1 minus modulus of Z2. This always happens. You know very well this thing is called triangle inequality, and this thing is called the reverse triangle inequality. Both are okay. These are triangle inequalities. So triangle inequality. And then what we call parallelogram law. What is that? So that is Z1 plus Z2 modulus squared plus Z1 minus Z2 modulus squared is same as 2 times Z1 modulus squared plus Z2 modulus squared. This is what we call the parallelogram law. And if you want to compare this thing, it is better to compare with this formula. A plus b whole square plus a minus b whole square is 2 times a square plus b square. And I think we do this in very basic classes. Okay, and one thing else, the argument of Z1 times Z2 is same as argument of Z1 plus argument of Z2. Are you okay with this thing? And if you divide two complex numbers, their argument is going to be subtracted. And if you are not getting this idea, then it is very simple. Like, we can discuss this thing geometrically, but we can discuss this thing in another way as well. Like, let us say our complex number Z1 is R1 E times I theta 1. You can write any complex number in polar form. So what is R? The modulus. What is theta 1? It's the argument. And what is this complex number? R2 I theta 2. You are going to find its argument. Then you can say that it is same as the argument of R1 times R2 e raised to theta 1 plus theta 2. Am I okay up to here? I'll just multiply. So what is the argument of this complex number? This is a complex number. E raised to I, what is the angle?
Cos alpha plus beta.
No, what is the angle? Theta 1 plus theta 2. So argument of this whole complex number is theta 1 plus theta. But what is theta 1? It's argument of Z1. What is theta 2? It's argument of Z. So you have this quantity. So you can write in polar form, and you can simply see that, okay, why this thing is same as this thing. Okay, but let me tell you one thing. Related to this, we have an idea. The principal argument of Z1 times Z2 is not same as the principal argument of Z1 plus the principal argument of Z2. Why? Why is that so? What is this argument? It's a generalized angle simply. But what is this argument? It's between minus pi and pi. Let us say this argument is exactly pi. Because we have already written it can be pi, but not minus pi. Because we have written greater than minus pi and less than or equal to pi. Okay, this is pi. This is pi as well. So pi plus pi. And this is also principal argument. Now principal argument is going to be 2 pi. It's not possible. So this is the counter example. It is not possible. This is possible in some cases, not always. Possible in some cases, not always. So what are those cases? The cases are if the real part of Z1 is greater than 0 and real part of Z2 is greater than 0, then we can say that argument of Z1 times Z2 is same as argument of Z1 plus argument of Z2. Now it's true. Can you tell me why? Why is that so? Real part greater than 0 means what?
Positive.
It lies in first or?
Yes, sir.
So, first means what is the maximum angle? Let's say 89. And this one means what is the maximum angle? Minus 89. Okay. So when you add these two angles, what happens? It is going to be either 89 plus 89, something like less than 180, and this thing becomes greater than minus 1. So you have that. So this is the idea that whenever this thing is there, then we can say that okay, this particular thing is right, otherwise it is not. Like if the real part of Z1 is greater than 0, then what happens? Then argument of Z1 is always greater than minus pi by 2 and less than pi by 2. Are you agree with this thing? If real part of a complex number is greater than 0, then its principal argument would be between minus pi by 2 and plus pi by 2. And the principal argument of Z2 is also between minus pi by 2 and plus pi by 2. If you add these two things, then the sum of this one is going to be argument of Z1 plus argument of Z2, which is between minus pi and, because when you add these you get minus pi, when you add these you get plus pi. So then you can see this is okay. And we know very well the principal argument is between minus pi and plus pi. Then this thing is okay, otherwise not. Okay, any question? Okay, can you say this thing? Is it possible? Not possible. Why? Like drawing में okay, so I think it is not possible. So we say that the set of complex numbers is not an ordered field because we cannot define any order relation on that. So one thing is good about the set of complex numbers is that it is algebraically complete, but one bad thing, it is not an ordered field. Okay, because you cannot define order in R2 exactly, because set of complex numbers is what we say isomorphic to R2, and we cannot define any order relation in R2, hence we cannot define any order relation in the set of complex numbers. Okay, so C is not ordered field. Order means you can exactly define that. Okay, if you take two numbers from a set, let's say E, then you can exactly say that okay, one is less than the other, greater than the other, or they are exactly equal. This is what we call the order relation.
Yes, sir.
Okay, if you cannot say about, but basically we don't have any idea like this. Only these two will work. If you say one is less than the other or greater than the other, we call it order relation. Otherwise, there isn't any.